So the first lecture we have is called The Derivative and Change Part 1. And we want to ask this question. What is a derivative? So this is a simple idea. Let's pretend that we have a function, f of x. So here's my x-axis and here's my y-axis, and I have this function, f of x. And what I can do is I can look at a point on this function. So here's a point right there on that function. And if you notice that each point on this function, you can kind of associate what's called a tangent line. Right? There's a rate of change basically. So we can take this sort of line that just kisses this one point right here, and we call this the tangent line. The derivative at this point gives the slope of the tangent line. So a derivative is really just a rate of change. Right, so when I say derivative, what you should think is rate of change. So I say derivative, you say rate of change. I say rate of change, you say derivative. They're the same word, really. So here, I can write on here if you want, if I had, let's say, 2. I could say f prime of 2, right, which is the derivative at 2, is just equal to the slope of the tangent line, whatever it might be. It just tells us basically how the function is changing, at what rate is the function changing at that point. And again, so I say derivative, you say what? Rate of change. I say rate of change, you think, again, derivative. So over here you can see what is the derivative? It's rate of change. Sometimes we also call this the instantaneous rate of change. We experience the derivative every day when we drive to school. It's called the velocity of the car. In some sense, you can actually graph, if you wanted to, you could graph the time you're driving versus the distance you go, d, and you'll see you actually get a graph right, wherever you're going. And the rate of change here, the derivative, is actually the velocity. So if you look at a point, let's change colors here, let's take blue. And if you look at a point here, there's a rate of change, and that's how fast you are traveling. The slope of that tangent line gives you the velocity. So if I give you a distance function and you take the derivative, you get the velocity function. And interestingly enough, if you take the derivative of the velocity function, you're going to get the acceleration function. And this is how this idea was originally discovered. You had a distance function, you take the derivative, you get the velocity function. If you're given a velocity function, you take the derivative, you get the acceleration function. I can also think of it as the slope of the tangent line. So whichever one feels better to you, in some sense, instantaneous rate of change or slope of the tangent line. But better yet, I say derivative, you say rate of change. I say rate of change, you say derivative. Now there's some notation we have to be a little familiar with here. So there's 2 types of notation. There's what's called prime notation and d notation. So let's look at the prime notation first, because I've already actually used that. So if you give me a function f of x, we can talk about its derivative, f prime of x. Right, so this is said the derivative of f with respect to x. And this is the prime notation. There's also a d notation. The d notation, it means the same thing. It's just written dy dx. Or in this case, if we're using f, we'd write df dx. And it said df dx. Again, it's just the derivative of f with respect to x. Right, they're really the same thing. It's sort of like the difference between writing my name in print versus writing my name in cursive. One is better at different times. As an example, you can think about a function like car insurance. Right? So car insurance depends on different things. It depends upon how old I am. It also depends upon maybe how much my car costs. So what you can do is, up here you have this prime notation. So if you know your function, your car insurance, if it's only dependent upon age, it's great. So when you write like f prime of x, you're saying how does your car insurance change with respect to your age. But we know that car insurance changes with respect to other things too, not just my age, but also, like I said, the price of the car. So this notation down here, when your function depends upon lots of things, is actually better. Because I could say, okay, for my car insurance, let's call it DI for insurance. So DI dt, right? How does my car insurance change with respect to my age? Versus, I could also talk about how my car insurance, so DI, let's say DP for the price of my car. How much my car costs. It's also going to change. And so that's where this notation becomes better. But in the beginning, we're going to use this notation because it's basically just easier to learn. And later, we'll kind of switch, over to this D notation because it is better in the end, especially if we have more than one variable. Okay, so let's talk about, before we talk about the definition, let's look at an example. So let's come up here and take a look at an example. And so example 1 says basically, let's look at Google's stock price, S in dollars, and be given as a function of t years after 2005. And what does S of 5 equal 600 mean? So this is actually from exam 1. And so S of 5 equal to 600. Remember, this is functional notation. And so the 5 is the input, and the 600 is the output. And you have to come back to the question and realize that S, well, the reason they chose S was because it's Google's stock price. And so S is in dollars, whereas the input, T, is in years. So this 5 means 5 years after 2005, and the 600 is actually Google's stock price then. So this says that Google's stock price in 5 years after 2005, say in 2010, was, and we have $600. So that's just basic functional notation from exam 1. Part B says, what are the units of S prime of t? So now remember, I say derivative, you say rate of change. So S prime of t is the rate of change of Google stock price. So try to understand what that means and understand it from the context. Right? Google stock price, it goes up, or sometimes it goes down, and sometimes it goes up really fast, sometimes it goes down really fast. And so we care about how it's changing, and S prime of t gives us a measurement of this rate of change. Is it going up really fast, or is it going down really fast in some sense? So S prime of t, and we can use actually a D notation to help us here, so ds dt, and then it becomes obvious that S is on top, which is output stuff, which is dollars, so I have dollars on top, and then on bottom I have time, which is in years, because t is the number of years after 2005. And so the units of S prime of t are just dollars per year. And then it makes sense. Yeah, Google stock price goes up, it goes down. The derivative, right, the rate of change of S, is just simply dollars per year. Just like if we talk about distance, we're going a certain number of miles, and so if we have a distance function and we take its derivative, we get miles per hour. Part C says, what does S prime of 5 equal 100 mean? Okay, again, this is functional notation, but now we have this prime, which means the derivative. So this is the derivative of Google stock price 5 years after 2005, and it says it's $100. So I could write something like Google stock price was changing at a rate of $100 per year in 2010. So let's write it like that. So let's write it like this: the rate of change of Google's stock price in 2010 was, and we can just say $100 per year. Sometimes people like to say was increasing at $100 per year, but I think $100 per year, it's sort of obvious that it's also increasing. And this brings us to another point. If you know the derivative is positive, and I say derivative, you say rate of change. If you know the derivative is positive, you know the function has to be increasing. I mean, think about this in terms of Google's stock price. If we know the rate of change at Google's stock price is $100 per year, that means it's going up on average, or in some sense, in this case, instantaneously, at $100 per year. If it was negative $100 per year, it wouldn't be going up, it would be going down. So the derivative gives us a measurement of increase or decrease. And we'll talk more about that a little bit later. And then finally, part D, let's do that right over here. What projection might one make about Google's stock price 3 days after t equals 5 years? Okay, so the idea is we kind of know what's happening right here at this moment. S of 5 is equal to 600. We know how it's changing as prime of 5. We know how Google's stock price is changing. It's changing $100 per year at that very instant. And so what we can do is to estimate S of 5 plus 3 days later. Right, what would this equal? Well, it should be equal to S of 5, right, and it's approximately, so I shouldn't say equals, this is approximately. So approximately S of 5 plus the rate of change, so how it's changing, as prime of 5. And how are we changing? We're changing by 3 days. So here we have to be a little bit careful. So it's times, and it's not just times 3. If you multiply by 3, this would be years, and it's 3 days. So we just multiply by 3 divided by 365. All right, so basically, you're multiplying by the change in time. In fact, why don't I put here first just the change in time? And then we can fill in what each of these things are equal to. So change in t. And so this is then equal to, well, S of 5 was 600. So you have $600. So, and that's a good approximation. So 3 days later is about $600. But even a better approximation is we know how it's changing each year. So we know it's changing by $100 each year. And now we're only going by 3 days. So we have to convert 3 days into years. Notice how the units cancel. Right, so this is year stuff, and 100 is actually dollars per year, so the years cancel and you get dollars back. And so this is going to be approximately, and I'll need my calculator to do this, so take out your calculator, and we do 600 plus 100 times 3 divided by 365, and we get out approximately, $600 dollars and 82 cents. So that would be my estimate for how much it's actually worth. So hopefully you feel comfortable a little bit with what the derivative is, in the sense that I say derivative, you say rate of change. The two different types of notation, f prime of x versus df dx. And now we want to talk a little bit about the actual definition of the derivative. All right, so how do we actually define the derivative? And if you think about it, we define this a very natural way. In some sense, we use what's called the average rate of change. If you've recently taken a college algebra class, we typically call this the difference quotient. And so the way we're going to do this, let's take a look at a picture first, and so you can see how natural it really is in some sense to define the derivative. So here's my function f of x. On this function, I'm going to need 2 points. So I'm going to give you 1 point here, which I'm going to call x, comma f of x. So input, output. So right here is x. And then I'm going to need another point. Let's make it in blue. And I'm going to put it right up here. And this point is going to be x plus a little bit more, so plus h. And so it's given by x plus h, comma, the output, f of x plus h. So suppose here I want to figure out what the slope, and I'm just going to approximate this tangent line. What's the slope of that tangent line? And I want to approximate it. Well, one way to approximate it would be to use this red point and this blue point. And so what I can do is I can compute the slope of this line in black that goes through the red and blue dots, and I can use that number to approximate the slope of the green line. And remember, the slope of the green line is really this f prime of x, the derivative of f at x. How is a function changing at x? It gives me the rate of change. I say derivative, you say rate of change. And so the way this works is you just take the slope of this black line, and remember, the slope of this black line is just the rise over the run, and the rise is simply a change in the output. So f of x plus h minus f of x, all divided by the change in the input. So x plus h minus x. So this is just the rise over the run. So those of you that remember, finding the slope of a line, the way that we do this is we just take the rise right here and divide it by the run. And there's actually a triangle right here you can see. And we're just taking the rise, which is this distance right here, f of x plus h minus f of x, and we're dividing it then by this distance right there. And so let's do like this. So we have this distance right here, and then we're dividing it by this distance right here. And now notice what happens to the x's down here. They're going to cancel. So normally, instead of just writing the x's out, what we'll do is we just get rid of the x's because they cancel, and we have f of x plus h minus f of x all divided by h. And this is approximately the derivative. Now I say approximately because, of course, the blue point isn't right on the red point. But as you let h get smaller and smaller and smaller, right, as h approaches 0, which means this blue point will start approaching this red point, this number that you compute here is going to get closer and closer to the actual derivative. And if you think about that language, as something approaches, as x approaches, or as something approaches something, what does the other thing approach? What does the other something approach? That's really this language of a limit. And so we can turn this into an equality if we slap a limit on it. And so the definition of the derivative is given by, so the derivative of f at x is equal to the limit, and you just let h go. It gets smaller and smaller, so let h go to 0. And this is what we mean by the definition of the derivative. It's really a very simple idea. Notation makes it look rather complicated. But it's just saying, hey, compute this difference quotient, which is really just this average rate of change. Okay, so compute this difference quotient right here, and you get out a number, and then compute it again as h goes to 0. And as h goes to 0, you're going to wind up getting this derivative. So let's take a look at some examples. So how can we estimate the derivative here? All right, using a table and then we'll look at an example of a graph, and then we'll look at a formula. Okay, so let's use this definition now to solve some problems. Right, what we're going to do is we're going to use the definition and really the average rate of change to estimate the derivative at a point. And so example 2 says, hey, use this table to estimate f prime of 1. And so remember this definition, f prime of x is equal to the limit as h goes to 0 of this difference quotient, which is a fancy name for, hey, just take the average rate of change, the change in the output on top, divided by the change of the input on the bottom. And it just turns out to be h because, again, the x's cancel. If you take x plus h minus x, you just get h back. And so if we're looking at 1 here, what we really care about is this stuff here. And if we want to let h go to 0, we'll first look to the right, and we'll look at these numbers. And we'll calculate the average rate of change between those two data points. And then we'll look, instead of to the right, we'll look to the left and calculate the average rate of change between those two data points. And then to get a good estimate, we'll add the two numbers together and divide by 2. So let's write this down. So what I can do is just say, okay, I'm going to take the change in f divided by the change in x. And the first one I'm going to do is I'm going to do f of 2 minus f of 1, all divided by 2 minus 1. And you can look at the table, and so that's just 7 minus 5. So f of 2 is 7, minus f of 1 is 5, all divided by 1, and I get back 2. So if you look to the right, it's changing by 2. Every time you go over 1, it seems to be going up by 2 on average. Right? So on average, it's increasing by 2. It may go down a little bit, but overall, on average, it's going to go up by 2 if you go to the right. Now, if I go to the left, it's going to do something else. So let's look at the new average, so change of f over change of x. So this delta, remember, it means change in. And so I'm going to do f of 1 now minus f of 0. So it's a change in the output divided by 1 minus 0, which is my change in the input. Again, I look over here, and I guess maybe I should use green since I circled these numbers in green. So f of 1 is 5, and f of 0 is 1. So this is going to be 5 minus 0. So it's going to be 5, I'm sorry, not 5 minus 0, but 5 minus 1, all divided by 1, which is equal to 4. So the idea of this is if you go to the left one, you're going to go down 4 on average. And so to find a good estimate, what we want to do here is we can say f prime of 1 is approximately, and we'll just take 4 plus 2. Those are the two average rates of change that we found, and we'll divide this by 2. And so that's 6 divided by 2, and so that's equal to 3. Okay. Right now that 3 doesn't have a lot of meaning to us. We could change this by interpreting, x to be in maybe years and f to be in dollars. And then when you take the derivative, it's output over input. So this turns out to be dollars per year. And now it kind of makes sense to us. This tells us on average we're going to change by $3 per year. So we're not decreasing, we're actually increasing. And you can see this if you look at the data here. You see that, yeah, f is certainly increasing here to here, but then it suddenly does what after it? Then it suddenly starts to decrease from here on. So if you look from here on, you see, oh yeah, it's decreasing. Right. We didn't capture that activity because we just looked at numbers around here. Right. That's all we cared about. What's f prime of 1? Okay, let's look at the next example where we use a graph to do this. And so now we want to use a graph to estimate again f prime of 1. So f prime of 1, remember, it's the slope of this tangent line, so I can see it now, what it's supposed to be. And so to do that, I have this definition, remember. I have this f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x, all divided by h. And so what this says is, hey, if you want to figure out what the slope of this tangent line is, what you need is to look at this point and try to find a point close by to it. And so if you look real close here, you're going to see that there's a nice point right here. And we know the height is 6. We just got to figure out the input. So here's the input down here. And it looks like these are broken up into 5 pieces. And so this should be 1.4 should be the input. And so what we can do is say f prime of 1 is approximately, and we can just use this point. Okay, the input is 1.4. Oops. I didn't mean to put a parenthesis there. I meant to put a comma. So input's 1.4, comma, output 6. That's the red point. And of course, the black point, the input is 1, and the output is some nice number between 4 and 6, so 5. And so we can basically, if you want, you can think about connecting these 2 dots with a line and just find the slope of the line, but it's just this average rate of change between these 2 points. And so this is going to be the change in the output. And so let's be fancy. Let's use functional notation. So f of 1.4 minus f of 1, that's a change in the output, divided by the change in the input, so 1.4 minus 1. Notice how these correspond real fast. My f of x plus h, that's really my f of 1 plus 0.4. And then my f of x is just this f of 1. And now down here I just have h. So I just have h down here. Now here it's a little bit hidden because I have x plus h minus x. So think about this, right? Remember, there's an x plus h here and there's a minus x. We just don't write it because the x's cancel. So this is my x plus h, my 1.4 right here. And this is my minus, x, my minus 1. Okay, so back to it. I know the output, if you plug in 1.4, the graph tells me that I'm going to get out 6. And if I plug in 1, the graph tells me I get out 5. And on bottom, I have 0.4. And so this is equal to 1 divided by 0.4. And my calculator will tell me that this is equal to, I think it's what, 2.5? Yeah, 2.5. I should check it. My basic arithmetic is always bad. So let's make sure. So 1 divided by 0.4, which equals 2.5. You could also turn 0.4 into 4/10, and then I know, yeah, that's, and you multiply by the reciprocal and certainly get back to 2.5. Okay, 2.5, now remember, I say derivative, you say rate of change, so 2.5 is how the function is changing on average. Again, you can give these, you can give this graph units if you want. So like down here, I could say this was years. That's my input. My output is dollars. So this is telling me on average I'm changing by about $2.5 per year when my input is 1, right, after 1 year. Let's take a look at the next example. So just so you know, we did a table. Right, we did a graph, and now we're going to do a formula. These are 3 different ways to represent functions, 3 very popular ways. Tables are used in Excel, and from Excel we typically make graphs, which we use in meetings to explain various ideas. And the formulas are typically in the background, running all the time. And so for a formula, in some sense, it's the easiest one to use. Oops. And so, again, let's write down the actual definition, f prime of x. The derivative of f of x is defined to be the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. And if I want to use this definition, what I can do is I can say to myself, okay, well, I'm just going to plug in a number. I'm going to let h be really close to 0. And so what that means is I want to plug in a number really close to 1. Because if h was like 0.01, that means that x plus h in this case is 1.01. So f prime of 1 would approximately be, and let's just plug in 0.01. So I'll do f of 1.01 minus f of 1 That's a change in my output. And then I'll divide this by 1.01 minus 1. Again, let's make sure you understand the parts. The x plus h is the 1 plus 0.01. And the x part here is just the 1. And again, I picked a number really close to 1, so it should give me a very good approximation to how the function is changing there. On the bottom, now I don't just have h, but remember there's an x here we don't write because they cancel. So there's x plus h, and then there's a minus x. And normally you don't write it because they cancel. The x plus h is the 1.01, whereas the x is just that minus 1. And now to figure this out, what I can do is just plug it right into the formula. So this is going to equal then, I'm going to plug in minus 1.01 quantity squared plus 5 times 1.01 plus 1. And then I'm going to take off when I plug in 1. So minus 1 squared plus 5 times 1 plus 1. And then all divided by a 0.1. And I'll need my calculator to do this. So I'll take out my calculator. Let's clear this out. And I'm going to do left parenthesis because it's all on top, negative, left parenthesis 1.01, raised to the 2, plus 5 times 1.01 plus 1. Then minus left parenthesis negative 1 raised to the 2 plus a 5. I'm going to do 5 times 1. And then plus a 1 in parenthesis divided by 0.01. And oops, I made a mistake over here actually. For some reason I put 0.1 on the bottom, so if you caught that, then you probably have it right. I should put a 0.1 here. So let me put a 0.01. And then I hit enter on here, and I get out about 2.999. All right, so this is over here. This is 2.99. And so I can actually probably guess at what the derivative is going to be if I had to guess here, because 2.99 is really close to the nice number of what? I bet you this derivative is actually equal to 3. And if I want to get a better approximation, instead of taking 0.01, I could take 0.001. So on my calculation, on my calculator, I could come up here and add a 0. So second insert 1.001 and come down here and just check it real fast. So second insert, put a 0 there. And then on the bottom, of course, that 0.01 will then become a 0.001. And again, I get 2.999. And you could do it again and again. And just like you did limits on the last exam, you can do them here too and realize that the derivative of this function at 1 is equal to 3. Now you can do other derivatives. You can do, f prime of 2, f prime of 3. You can do f prime of any number that you like, really, and use the same sort of idea here and try to figure out, what the derivative at that point might be. Okay, so we were just talking about a derivative at a point. Now we want to talk about derivative as a function in general. So what happens not just at one point, but what happens at all the points when we take them into consideration. So just as an example, let's look at example 3 here. We want to sketch the graph of f prime of x given that this is f of x. So think about this. We can draw an x and y axis here. And what we want to do is graph f prime of x. And now we're not going to do it at a single point like just one. We're going to do it at all the points. And if I say derivative, you're supposed to think what? Rate of change. And so really you're saying, if you talk about the derivative of this function, you're saying, what is the rate of change of this function? And this is a line. And we know on the line, the rate of change is given by that letter m, which we call the slope. And the slope is constant. So when I look at this, what do I know is that if the rate of change is constant, and rate of change and derivative are really the same thing, that means the derivative is constant. And it's equal to the slope. And so the slope of this line, I'm not sure what it is, but it's certainly going down, so I know it's not positive. It must be negative. And so what I would do here, for the derivative, I would just draw a horizontal line, because that's what it means to be constant. And if I put numbers here, you could actually tell me what it was. Like if I put a 4 here and a 2 here, right, so that was 2, and that height was 4, you could tell me then the slope of this line. And here to be a little bit careful, yes, it's rise over run, so 4 over 2, but because it's going down, it's not positive, you put a negative sign, so it's equal to negative 2. And so over here, I could put a negative 2. So if I gave you those points, then you could actually draw it exactly on the other side. Now, that's an easy one, and it works for all lines. So if you give me a line as the function, then you can always tell me the slope, because it's just, you can always tell me the derivative because it's just the slope of that line. Let's look at the next example, example 3, and we want to get a sketch a graph of f prime of x. So first we can draw this x and y axis. So here's the x, and here's the y. And now this one's a little bit harder. So to do this one, the idea is that the rate of change is changing all over the place. It's not constant. You can see at this point here, if you want, it's going up, so the rate of change better be positive, whereas over here at this point, the rate of change better be negative because it's going down. The rate of change that we really care about, though, is when it's 0. And so that's what we want to plot first. So if you see, there's just one point where you have 0 rate of change because the tangent line is horizontal. And when the line's horizontal, it means it has no rate of change. And if you know that, so here, you know, the slope is 0, the tangent line. Right? The slope is 0, that means the rate of change is 0. I say rate of change, you say derivative, so that means the derivative is 0 at that point. So what you can do is come over here, and if you're doing f prime of x, you know it passes through 0 right there at the origin. So this is f prime of x. And then if you look to the left, you see, oh, the function's, you know, going up, it's increasing, and so all the rate of changes must be positive. And again, you can look at one point and ask yourself, you know, what's the rate of change of that tangent line? So what's the slope of that tangent line? And it's positive because it's going up. And so what I would do to the left, I'd say, oh, the derivative must be positive, right? Because the derivative is the rate of change, and the rate of change is positive over here on the left-hand side of the function. On the right-hand side now, it's going down, so the rate of change is negative. So over here, I say rate of change is negative, it means the derivative must be negative. And then I think of a very simple way to connect the positive, that dot, and the negative. It's very simple. It's just a nice looking line going through all the points. Again, that's supposed to be a line. And so it's a nice line going through those points. Let's do the same thing here with this graph. So this one's a little bit harder. Right? So they kind of build in complexity. And so we can draw the x-axis. We can draw the y-axis here. And what you want to notice, if you want to figure out what f prime of x looks like, you want to notice that right here, right, that's where the slope is 0. And also right here. And so over here, I'm going to plot those 2 points. So I'm going to put it right here. There's where it's 0, and about the same distance on the other side, it's 0. And I notice the function then is going down on the left here. So if you look over here on the left, it's going down, so that must be negative. If you look in between, let's use a different color. Okay, so if you look over here to the left at these points, right, the rate of change is negative. If you look at a point in between the 2 red dots, it's going up, right, so the rate of change is positive. And finally, if you look to the right of that last red dot, it's going down, so the rate of change must be negative. And again, I'm saying rate of change. When I say rate of change, you say derivative. So that means on the left of these points, the first point, it has to be negative, so I better not be up there. I better go down here on the bottom. Right, so it's negative. And then it goes positive, so it's positive in between here. And then it goes negative, because the rate of change is negative. And so these all match up. So notice how nice, negative, positive, and negative. And I got to figure out, how do I connect, these minuses and pluses and dots in a nice, easy way. And it's exactly what you would think. Okay, you just start down here and try the best you can. Go through all these points, and it's a nice looking upside down parabola. That's what it's supposed to be. All right, the last problem we're going to do, again, we're going to use this definition of the derivative, and we're going to use it more precisely. And so let's take a look at these examples. So we're going to use the definition of the derivative to find f prime of x. And we're going to do two examples. The first one, part A, is just f of x equal to 3x squared. Right. Later on, we'll learn some rules to do this, and you'll find out that it's actually really quick. We'll learn what's called a power rule, and you'll realize that this f prime of x is just going to be equal to 6x. In some sense, we'll learn that the 2 comes down and multiplies by the 3, and we just take 1 away from the 2, and you just get this 6x back. Now, we'll do that next week. This week, we want to practice using the definition. Right, we want to make sure, basically, everybody can do what this says. So the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Right, the first step, and this is one of the hardest steps for students to get. Right? One reason why it's hard is because sometimes students think that this x and this x are the same, but they are not. Okay, the reason we use x is because it's a letter of our alphabet, and it's a symbol we're all familiar with. But really, x is something just like I don't want to say a placeholder. I mean, it's just a holder for a rule. So when I look at this f of x, I remember it's just a rule. It says whatever's inside here, I square it and multiply it by 3. And it can be whatever you want. So, and sometimes it's to your advantage not to think about it as being x. Think about it being something else, like a smiley face. So if a smiley face is inside there, I know I take smiley face and I square it, and I multiply it by 3. And if you think about it in these terms, you'll start understanding that a function is really just a rule. And the reason we use x is because it's a symbol we're familiar with, so we can write down the rule in a nice, concise way. And so over here, what I'm going to do is I'm going to write down the limit as h goes to 0 and do what this says. This says basically wherever you see an x, plug in an x plus h, or wherever you see a smiley face, plug in an x plus h. So this is smiley face squared times 3. So it's going to be x plus h squared times 3. And you can use the language, oh, it's smiley face squared times 3, or 3 times smiley face squared. So if that's x plus h, it's 3 times x plus h squared. Right, then minus f of x, and you guys are usually good at this one, so you just write down 3x squared. And the bottom's fine. It's all divided by 3h. And now we have to figure out, we have to evaluate this limit. And so we did limits on the last exam, but this one's a little bit different. Instead of x going to 0, we have this h going to 0. And so what we need to do is we need to plug in, like we did before, just h equals 0. The problem is, if you do plug in h equals 0, you're going to get 0 on top and 0 on the bottom, which is an indeterminate form, which means you cannot determine the limit as given, so you need to do a little bit more work. Basically, we need to do some algebra, and then we can figure out what this limit is. So the algebra we need to do is we need to multiply out this x plus h quantity squared. And so this is going to be 3 times x squared plus 2xh plus h squared, all minus a 3x squared divided by h. Now I'm going to explain to you where I got this x squared plus 2xh plus h squared. So remember, if you have x plus h squared, what does this mean? It means you have x plus h times x plus h. And so you're not going to get just x squared plus h squared, because you're going to have this middle term, because when you multiply this out, when you FOIL it, you're certainly going to have an x squared, but you also have an x plus h. And then when you hit the next term, you'll have an hx, so plus hx, and then you'll have also the h squared. And so in the end, what you get here is an x squared plus 2xh plus an h squared. And so that's where this term right here comes from. All right. And so now we're going to multiply through by the 3. And so I get the limit as h goes to 0 of 3x squared plus a 6xh plus a 3h squared minus a 3x squared, all divided by h. And then what's going to happen to those 3x squareds? Well, they're going to cancel because you have plus and you have minus. And so then this is going to equal the limit as h goes to 0 of 6xh plus 3h squared, all divided by h. And now here you might think I can evaluate the limit again. I did cross something off, but when you plug in 0, you're going to see this first term's going to be 0, the second term's going to be 0, and so is the bottom term. So you're still going to get that 0 over 0, that indeterminate form. So there's more algebra we need to do. So it's equal to the limit as h goes to 0. And what we can do, or as you were trained, we can pull out what they have in common. And I'm just going to pull out the h. So I'm just going to pull out this h because you'll see why here in a minute. And I get 6x plus 3h, all divided by h. And again, the h's, well, I shouldn't say again, but here something else is going to cancel, so the h's are going to cancel. And so then this is going to equal the limit as h goes to 0 of 6x plus 3h. Now if you plug in 0, you're going to get the answer. And the reason you're going to get the answer is because back here, when we canceled off these h's, that's where we got rid of that indeterminate form. That 0 over 0 went away. And so this is going to be equal to then, we plug in h equals 0 so I can drop off the limit. So I have 6x. Right, notice I'm plugging in h equals 0, not x equals 0, plus 3 times 0. And that's just going to be equal to 6x. And so the derivative, f prime of x, is 6x. This is a very important process to go through. If you cannot do this, you will struggle tremendously later on. Because if you can't do this, there's a problem with your basic algebra skills. And so we need to make sure that you can do the algebra so later on you're not struggling with it. Let's do the last example here, part B. So on part B, I have g of x equal to 1 over x. So let's not get stuck on f, right? So I can say g prime of x. There's no big deal between f and g, so the same idea. Right? Why do we use f? Because it stands for function, and then we use g because it's the next letter in the alphabet. So I have g prime of x is equal to the limit as h goes to 0 of g, almost said f, of g of x plus h minus g of x, all divided by h. And so this is equal to, this is the first step where students typically stumble, and if you can do this, usually good here on out. So remember, g is just a rule. Right? G of smiley face is simply 1 over the smiley face. And so g of x plus h is simply, let's keep the limit on there, shouldn't drop that off. The limit as h goes to 0. So g of x plus h, again, think of smiley face. G of smiley face is 1 over smiley face. So g of x plus h is 1 over x plus h. And it's the whole thing on the bottom. Right? Not just the x and then plus h. It's the whole thing. Whatever's inside here goes down here. I mean, look. Whatever's inside here goes down here. So this is inside here, so it goes down here. That's the idea. That's the rule. That's what it tells me to do. Then minus g of x, which is 1 over x, all divided by h. Now again, you can plug in h equals 0, but you're going to get that indeterminate form out 0 over 0. And the way we get rid of this is you're subtracting fractions. So you know when you subtract fractions or add fractions, you always need to find a common denominator. And finding the common denominator is real good. Real easy. I have x plus h and I have x. So what I'm going to do is I'm going to put an x down here And if I put an x down here, I better put an x up on top. So there's my x on top. And then over here, I'll put an x plus h. And then I better put an x plus h on top. So I'm just turning that 1 into an x. I'm just writing x for it. And I have an x plus h on top. And now I can add the two fractions because they have a common denominator, in this case x times x plus h. So the limit as h goes to 0, and then I have x minus the quantity x plus h on top. The common denominator is x divided by x plus h. And this whole thing is divided by h on the bottom. And then this is equal to the limit as h goes to 0. And then I have x, and I'll distribute that minus sign through, so minus x, and then minus a plus is a minus h. This is all divided by x times x plus h. And then that's all divided by an h. And what's nice now is that these x's are going to cancel. And so this is going to be the limit as h goes to 0 of negative h all divided by x times x plus h. And then this whole thing is divided by h. Okay, you can try again. Oops. You can try again to plug in h equals 0. You'll see again you're going to get out this indeterminate form. And so what do you do now? Well, you have to realize that over here, this h is really an h divided by 1. And so you can simplify this by thinking you're dividing by this fraction, h over 1. And we know that if you divide by a fraction, to simplify, you simply multiply by the, let's change that. So how do you simplify when you divide by a fraction? How do you carry out that operation? So think about that for a minute, and then I'm going to do it. All right, so I have the limit as h goes to 0. And so if you divide by a fraction here, to simplify, you simply multiply by the reciprocal. So this is a negative h on top divided by x times x plus h. And then I'm going to multiply by the reciprocal, which is a 1 over h. And then what happens to these h's? They're going to cancel. And so I get the limit as h goes to 0 of minus 1 all divided by x all times an x plus h. And now if you plug in 0, you're going to see you get the right answer. And the reason why that indeterminate form is no longer there is, look, you canceled out the h's. That's at 0 over 0 when you plug in. And so I'm going to plug in h equals 0. Right, notice I didn't say x equals 0. I'm going to plug in h equal to 0. And so this is going to equal then minus 1 all divided by, and then I have x times x plus 0, which is equal to minus 1 divided by x squared. And so that's my derivative. G prime of x is equal to negative 1 over x squared. Again, this is a bit difficult. It's a lot of steps, but each step there's a reason why I'm doing it. Right, so you have to do what it says. I come up here, I start with the definition, and I do what it says. It says to plug in x plus h, take off when you plug in x, divide by h. And the next step, I find the common denominator, right? Because again, if I plugged in h equals 0, I don't get anywhere. I get an indeterminate form, so I have to do some algebra. I find that common denominator. When I find a common denominator, eventually here, I'm able to cancel off the x's. That helps me out a little bit. It makes the expression a little simpler, but it doesn't solve the problem for me. Again, I could plug in h equals 0, and I still wind up with a 0 over 0 form. So then I realize that there's more algebra to do, so I multiply by the reciprocal, because I'm dividing by h over 1. Here, the h's cancel, and then I got it. All right, so I plug in h equals 0 one last time, and I realize I don't get an indeterminate form. And I'm plugging in h equals 0, not x, h equal to 0, and I get my negative 1 over x squared. Next week, like I said, we'll learn how to use these rules of differentiation, which will make this process a lot simpler. But for now, we want to concentrate on using the actual definition to make sure there aren't any issues with our algebra.